Welcome then to our introduction in Chapter 1, Lesson 1. In this lesson, your goal is to be able to describe the difference between inductive and deductive reasoning. Both are very valuable into geometry, working in geometry, but one of them might serve us better than the other. So your goal today is to find the difference between them. So I have a mind trap here which requires you to do a little bit of thinking and try to answer this question. You should pause the video right now and think about this one and see if you can figure out whether the Z, which is not pictured there, should be above the line or below the line. So go ahead and press pause, think about it, see if you can come up with the answer and a reason why. All right. I'm going to assume you thought it through, came up with an answer. Well, we'll see what that answer is, see if you're right here in a little bit. I want to take you back to grade school for a bit. If you remember the scientific method back in grade school, you would try to solve things or learn things in science about plants or animals or metal filings and so on. And so what you'd do is you'd make a lot of observations. You'd look at things that were happening. You'd gather a bunch of information and write it down. And based on those things, you'd make a hypothesis, which if you remember was an informed guess at what might be going on. You'd base it on your observations and the information that you'd gathered. So you'd make sometimes it could be called a conjecture, but then you would take that guess and you'd test it. You'd do experiments, which oftentimes were my favorite things. If the experiment backed up your hypothesis, and it happened enough times, well, some scientists then would be willing to say that they'd make a statement or they'd call it a law. Maybe you're familiar with a few laws like Boyle's law or Ohm's law. Well, in geometry, we do the same thing frequently. It's called inductive reasoning, and it's similar to the scientific method. If you recall the surfer and spotter problem that we did in class, we followed the inductive reasoning approach. We drew some pictures, drew some lines, we made some measurements, we gathered a bunch of information, we looked for patterns, we drew some conclusions. We thought, hey, maybe it's in the middle. But then we tested and found out, no, maybe that's not the best spot, maybe a little further over, maybe it's in the corner. We called those conclusions conjectures. And several times during the process, we found out that we weren't correct. Sometimes we were right and sometimes we were wrong on those two problems. And that's the problem with inductive reasoning. Oftentimes it can get us on the right track, but we can't always be sure we're right. Here's an example of that. You see an outline map of the United States. There was always a question, if I were to color this map, what would be the fewest numbers of colors that I would need to color this map such that no two states that share a border would be the same color? In other words, Ohio and Kentucky here would need to be a different color. Indiana, Ohio, and Kentucky would need to be 3 different colors, but Michigan could be the same color as Kentucky because they don't share a border. So people puzzled about this for years and years. They tried to color it in different ways and tried to come up with the minimum number of colors possible. If you want to pause and think about that a little bit, you can. See if you can come up with an answer that makes sense to you. Go ahead and pause it and come back when you're done. Here's another example of people coloring, try to limit the colors. I one time was kind of obsessed with this and I tried to draw a whole bunch of weird shaped maps to try to figure out how many colors. But as you'll notice from these examples, the most number of colors you'll ever have to use is 4. no matter how weird the map is, you can color any map in existence with 4 different colors and never break the rule of bordering states having the same color. Well, this was the way we went at it, was inductive reasoning, because we tried a bunch of examples. We looked at maps. We tried to color them. I know I did. I created maps and tried to color them. I was using inductive reasoning. I was making drawings and collecting evidence, making observations, tried to look for a pattern as I was doing this. I drew a conjecture. I had different numbers than 4, that's for sure, for a while. I thought I could do it in fewer, but I never did. That was using inductive reasoning, and we use it every day. There are other examples where you could come up with your use of inductive reasoning, and you probably didn't realize it. What might be some examples of using inductive reasoning? Well, one I could think of is, why am I getting bad grades? Well, I might think, let's see, well, the teacher is a bad teacher. The teacher gives too hard a homework. The teacher doesn't give me enough time. We can come up with a lot of conjectures that don't necessarily have proofs, and we don't know whether those are necessarily the reasons. Notice I didn't mention the student there. Maybe the student doesn't spend enough time. Maybe the student doesn't get enough sleep. Maybe there isn't time in the day at home for the student. There might be a lot of reasons. Inductive reasoning doesn't solve the problem for us necessarily. Looking at this mind trap here, inductively we might try some things like, well, let's see, above the line there are 9, 10, there are 14 above the line. Below the line there's 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe if I put it on the bottom, it'll be closer. They'll both be even numbers of letters above and below. Or maybe if I put it below, the number of consonants above and below are the same. Maybe that's what it is. We keep trying some different examples, but you can't really be sure. Well, that's where, oh, I just thought of another one here. Maybe B, C, and D, and Z rhymes with it. So it would go with those 3 letters on the bottom. Or it's in the last half of the alphabet. Z is near the end. It's actually at the end. So we'd put it with the other ones that are near the end of the alphabet, X, Y, and Z. Again, it's all inductive reasoning. Is there a deductive approach to something like this? Well, what is deductive reasoning? Excuse me. You start with statements that are accepted as true. Things that nobody would question because we know that they're absolutely true. And then we would use logic, would use those true statements to draw a conclusion. Whatever conclusion you come up with has to be true because you deductively use true things, so anything that would result from that would be true. Deductive reasoning, it's always logical, it's always valid. But inductive reasoning can sometimes lead you to a conclusion that is not true. Let's go back to that mind trap. Should the Z go above or below? We tried it inductively. What about trying it deductively? Are there any facts we can observe about this puzzle? And maybe you came up with that. If you'll notice that all the letters on the top have only straight line segments as part of them, whereas all the letters on the bottom have some curves in them somewhere. Well, if that's a fact that all the letters with straight line segments go on the top and curves on the bottom, we know for a fact that Z has to go on the top because it's made up of only straight line segments. That would be a deductive approach to it. Establish some true facts, use those to solve for an answer. I liken geometry to Legos. Well, how do I do that? Well, some of you have a lot of Legos, I know. You might have a lot of pieces of Legos. Maybe some of you have old tubs full of Legos. Well, what do you do with those Legos? You take those Legos and you put them together to make little figures. You make some small parts. And then you take those small parts, turn them into larger parts. And then those parts go together to make larger creations and larger. By the way, maybe you recognize this. It's by an artist whom our author Howard Jacobs uses a lot, M.C. Escher. Some disturbing things about this. There is a picture on the back of the wall in our classroom that you could see the actual woodcut that Escher did. But you take your Legos and make larger and larger and larger things. Well, that's what we do in geometry. We take parts, we take definitions and undefined terms. Those would be terms that we can't define very well. So we have those two Legos. We have postulates, which are simply statements that we're not able to prove. We just accept them as true without proof. We also have theorems. This is another important Lego in geometry. It's a statement that we have been able to prove directly, deductive reasoning. Some of those theorems turn into laws. And we use those laws, those theorems, the postulates, definitions, undefined terms to create an entire system. In this case, it's our system of geometry. So here's chapter 1, lesson 1. We're looking at some definitions in geometry. Our author uses the Nazca lines of Peru to demonstrate this. I like how he always makes it real. So the Nazca were Indians in Peru. And from a spaceship up high, we can see lines that the Nazcas were able to produce in the ground, miles long, perfectly straight, which is amazing in itself. But when you look into it further, you see that they've got a lot of different animals that they created shapes of using lines in the ground. So here's a map where you could find them in Peru. Here's one example, a hummingbird. Miles long. I didn't look, I should have. But you see how straight the nose of that hummingbird is, or beak, I guess, tongue, whatever. And you see the wings, look at how parallel the lines are, and they go out a long distance. And they were able to create some pretty cool looking drawings without the aid of a spaceship, or I don't know how they did it. There's a pretty cool flower symmetry, radial symmetry in the petals. Here you see some more, a monkey with a curved tail. Look how each of those lines is pretty close to the same distance from the previous one. A whale down here. You can look at more of those pictures at the link there. But he uses that to introduce the idea of points, lines, and planes. These are undefined terms. It's really, really hard, if not impossible, to define them, to explain them. We just use them to explain other things. Our author uses a map to demonstrate all three of these terms. So here's a map of a city. And you can probably notice some examples of points, lines, and planes. The end of this would be a point. Actually, every point along here is a point. That's actually what a segment is. A segment is made up of an unlimited number of points. I guess I could demonstrate that. Where's my pen? So if I were to put a point here and a point there, and then put a point halfway between, and then a point halfway between, and another point halfway between, they're kind of small points, maybe you can't see them. Another point, another point, another point, and I just keep putting points. If I put enough points in there, I end up with a segment, which will be straight, not crooked like I just drew it. So points are demonstrated here. Every place those roads meet, that would be a point right in there. Segments are also demonstrated. Segments have two endpoints. So from there all the way down to there would be a segment. There are a bunch of segments in here. There aren't really any lines in here, and you'll find out why later. Maybe you can figure it out. A segment is part of a line. A line goes on forever in both directions. So we can't really get true lines here, but we can get points. Plane, there's another one. A plane is a flat surface that goes on forever in all directions. This whole map surface would be considered a plane, but it's really only part of a plane, because a real plane would go on forever in all directions. That'd be a really big monitor. So points, lines, and planes are our first undefined terms. You look at points here a little bit, and you'll notice that these points are labeled with capital letters, and that's just a convention that we follow. When you label points, use capital letters. Can be any letter. Our author did a cool thing in our other book. He picked a theme each time, and like that might be Tim, or it might be, I was going to say Bob, but that's two B's. Maybe one day he'd do names, one day he'd do states, and he'd label the points to spell words. Here's a line segment and a line. So pause maybe a bit and think about these two questions. How are they alike? How are they different? Hopefully you paused and now you're back. A line segment, of course, it's made up of what? Two segments? Or I'm sorry, 2 points? No. 2 points are labeled, but there are an unlimited number of points there. So a line segment would be a set of points that has 2 endpoints. Whereas a line, it is also a set of points, and it's named by 2 of those points, but it goes on forever in both directions. You'll notice how we label lines with lowercase letters, points with capital letters, lines with lowercase letters. Do you come up with any other differences? Here's our next undefined term, planes. So what are some characteristics of planes? Well, they're flat surfaces, and this is only a part of a plane, but it is a plane. You notice we label them again with capital letters. They can be oriented in different directions. They're undefined. We just don't try to give them a definition, we just use them. Now realize now, as the year goes on, your book will call this a plane. It's a part of a plane, but we just call it a plane anyway. Same thing on this previous. We might call this a line sometimes, realizing it is a line segment. That doesn't happen as often. It's nice to call that one a segment and that one a line. So now that we've got some undefined terms, we can use those in some definitions. I wrote flashcards here because years ago I used to require students to make flashcards of all of these. I'm only suggesting it now, either real paper ones that you can use, word on one side, the definition, the meaning on the other side, or maybe you can do it digitally. It's up to you. But here are our first definitions. Collinear points. Think about what that might be. I see line in there. Co means with, so maybe collinear. Well, here's our definition, one that you'll need to know. Points are collinear if there is a line that contains all of them. Pretty straightforward. If I were to put a point up here, that would not be collinear with the other 3. Here are some non-collinear points. You could probably guess, based on this previous one, what the definition would be. Here it is. Points are non-collinear if no single line contains them all. So there is a line that contains them. There is no single line that contains them. Get these 2 definitions down. Collinear and non-collinear. So here we've got some coplanar points. Got to guess at what that means? And we've got concurrent lines. Think about some good definitions. Maybe pause it and make a guess. Okay, if you're back. Points are coplanar if there is a plane that contains them all. Hopefully you can see the similarity between collinear and coplanar. That'll help you memorizing. There is a line that contains them if they're collinear. There's a plane that contains them if they're coplanar. Concurrent, how you doing with wording on that one? Are points concurrent? No. Its lines are concurrent if they do what? How would you say that? Lines are concurrent if they contain the same point. If I were to, well, I might as well do it. If I were to draw another line up here, whoa, that's not very good. Is that concurrent at all? Well, it is with this one because they intersect. They contain the same point. And it is with this one right here because they contain the same point, but not with all of them. L, M, and N are concurrent because they contain the same point. Get rid of that. So, Chapter 1, Lesson 1, the assignment is Gradebook Wizard. And the problems. Here's a picture of a map, and you'll see that there are a bunch of segments in here. That's a segment. That's a segment. There's a segment. Is this a segment? Sure it is. It's got 2 endpoints on it. Is this a segment from there to there? Yeah. What if I went from there to there? Would that be considered one segment or a whole bunch? Well, if you use this as an endpoint here and use this as an endpoint here, that's one segment. So you want to keep that idea in mind as you work through some of these. I skipped some, so you don't really need to know about the length, the centimeters and the miles, and the scale. So here are some questions. Work your way through them. You're measuring in centimeters here. Following line segment in centimeters. Not millimeters, the smallest one, but centimeters. Just round it off to the nearest one. I think I skipped these. Alright, nothing particularly difficult here, but if you have a question, make sure you bring it to class tomorrow. Just a repeat of the map for that. This one gets people sometimes. Each point in which line segments intersect has been labeled with a letter. So I think we've got 9 different points, intersections labeled. Remember, there are more than 9 points pictured there. There are an unlimited number of points. We've just named 9 of them. I guess I gave you the answer to number 17. What does the word collinear means? You can get that. The figure has been drawn so that each set of points that appears to be collinear actually is. So there's no trick. B, E, and H appear to have one line that contains them all, and it does. No trick there. That's all that's meaning. So for example, and they give you E, F, and I as an example here. E, F, and I. They are collinear. So now with that in mind, they ask you some question. How many sets of 3 collinear points does it contain? List them. So you're going to have quite a few listings that are similar to EFI. And which one did I give you? BEH. That'd be another one. Just the definition of concurrent. Now, notice here. How many lines in the figure are concurrent at A? How many lines are concurrent at A? So there's point A. How many different lines? And now don't say lines go on forever. There aren't any lines. They're talking, of course, about something like this. A segment is part of a line, so that would be 1. And then there are other points. How many are concurrent at B? How many are concurrent at C? How about each of the other points? You might have a few answers here. Now some tricky questions about line segments that can be named using letters in the figure. Line segments, you'll notice. Here we were doing lines. Here we're talking segments. How many different line segments in the figure meet at point A? Name them. So here's point A. How many line segments named with 2 letters? So AD might be one. Ooh, AE is another one. So keep that in mind as you work through this. Name them. How many different line segments meet at B, how many at C, and so on, and name them. All right, this is set 3. It should say set 3 up there, and in this case, set 3 is sticky credit. What sticky credit is you can do it if you want. It's a challenge to those that want to challenge themselves a little bit more. There's no such thing as honors geometry for some reason, or AP geometry, but I would like to give those of you that are capable a chance to challenge yourself and reward you for that. A sticky credit then is a set of problems that I assign as sticky credit, and I assign a value to them. In this case, I think the assignment said maybe +5. So working on set 3, following all the directions, and I don't usually give a lot of help on that, but here's a little bit of it. Use a colored pen or pencil, draw in the 3 lines. Draw enough so that it crosses the whole figure. So you're going to be doing a little bit of drawing here. You create that picture, much larger though, and then draw in those segments that they ask. And there's from another one, and another one. And so I kind of worked through some of this, but that's what it looked like. And now they ask you to use inductive reasoning. What do you notice? What do you notice? And I called it inductive reasoning because we did several examples and then we tried to draw some kind of a conclusion. And then they ask you to change the shape a little bit, and answer some questions, and they end up with number 8, what do you think? What inductive conclusion are you going to draw? So that's it. Work through this assignment ahead of time so that you're able to ask questions in class. Thank you.